Welcome back to Specter AI. I'm Specter P. In this video, we're going to break down the BB84 protocol, one of the most important foundations of quantum cryptography. BB84 is how two parties create a secure, shared key using the laws of physics instead of relying on classical math or computational hardness. We'll look at what BB84 is, why it matters, how it's used in real-world quantum communications, and later in the video, we'll explore whether this protocol can be attacked and what its actual limitations are. Let's get started. In 1984, two researchers, Charles Bennett and Gilles Brassard, introduced a completely new idea. What if two people could create a secret key using the laws of quantum mechanics? Not math, not assumptions, but the physics of the universe itself. That idea became BB84, the first quantum key distribution protocol. And the goal is simple. Allow two parties to share a secret key with a security that can't be broken, even by future quantum computers. BB84 works by encoding information onto individual photons. These photons behave differently depending on how you look at them, which means any eavesdropper trying to intercept the key can't do it quietly. Their interference creates disturbances that Alice and Bob can detect immediately. So at its core, BB84 isn't just another encryption method. It's a way to generate a secret key that comes with built-in proof of security, guaranteed by physics, not software or algorithms. This is the foundation of modern quantum cryptography, and everything else in BB84 builds from this single idea. When two people want to talk securely, really securely, the first thing they need is a secret key. A key is just a string of random bits. But that little string controls everything. It encrypts your message, it decrypts it on the other end, and it's the only thing standing between you and anyone trying to read, steal, or manipulate what you send. Think of it like coordinates to a safe house, launch codes, medical records, or even your bank logins. If you trust the key, you can trust the message. If someone else gets the key, the entire system collapses. And that's exactly the problem BB84 solved in 1984. Bennett and Brassard asked a simple question. Instead of relying on math to protect a key, what if we use the laws of physics? What if the universe itself could guarantee security? In BB84, Alice starts by generating a sequence of random bits. Nothing meaningful yet. They're just raw material. But randomness is the foundation of every secure key ever created. Then, Alice encodes each bit into a single photon. To do that, she chooses one of two polarization bases at random, the plus basis or the cross basis. Think of these as different orientations she can use to encode the information. Each choice changes the quantum state she sends down the channel. Bob, on the other end, measures each incoming photon. But he also chooses his measurement basis at random. Sometimes he guesses the same basis Alice used. Sometimes he guesses wrong. When he guesses wrong, the measurement becomes meaningless, and that bit gets thrown away. When he guesses right, their results match perfectly, because the photon carries the information intact only when measured in the correct basis. After the transmission, Alice and Bob publicly compare nothing but their bases. They never reveal the actual bits. Wherever their bases match, they keep the bit. Wherever they differ, they discard it. The result is the sifted key, the first shared secret string of bits created using quantum physics. And here's the brilliant part. If anyone tries to intercept or measure the photons in transit, quantum mechanics guarantees they leave fingerprints. Eve can't look at a photon without disturbing it, and those disturbances show up as errors in the sifted key. If the error rate is too high, Alice and Bob know instantly the channel isn't safe. and they abort the session. So BB84 isn't just a way to share a key. It's a way to share a key with proof of security. A way to know, rather than hope, that no one else is listening. This slide shows exactly how that process plays out. Alice's bits, the bases they choose, Bob's measurements, and finally, the sifted key, the portion where both bases aligned. This is the beginning of quantum secure communication. Before we can understand why BB84 works, we need to talk about randomness, what it actually is, and why classical computers have never truly had it. When we talk about randomness in everyday software, whether it's Excel's rand function, or Python's random module, or any pseudo-random number generator, none of these are truly random. They're all deterministic formulas. They take an initial value called a seed, run it through a mathematical algorithm, and produce a stream of numbers that only look random. But if someone knows the formula, or the seed, they can recreate every value the system will ever generate. That's why classical randomness is often called pseudo-randomness. It's randomness that exists only on the surface. Even functions like Excel's rand are what's called volatile functions, meaning they recalculate every time the spreadsheet refreshes. But the randomness they produce still comes from a fixed internal formula. It's convenient, it's fast, and for everyday use it feels unpredictable enough, but it's not secure randomness. If someone knows the algorithm behind rand, they can reproduce the sequence exactly. Hardware randomness tries to improve on this. Many classical systems use electrical noise, thermal fluctuations, or clock jitter to gather unpredictable data from the physical world. These sources are messier and harder to predict, but they're still not fundamentally random. With enough measurement or the right modeling, noise can be biased, nudged, influenced, or even partially predicted. Classical noise never gives us pure unpredictability. Quantum randomness is different. It's not algorithmic and it's not noise. It comes directly from the laws of physics. When a photon is prepared in a superposition state and measured in a basis that doesn't align with that state, the outcome is genuinely unpredictable. There is no hidden variable holding the answer. There is no formula running in the background. The universe doesn't commit to a result until the moment you measure it. That's what we mean when we say quantum randomness is fundamental. And this matters in BB84. The entire protocol depends on true randomness. Alice's random bits. Alice's random choice of basis. Bob's random measurement basis. If any of these were predictable, if they came from a deterministic formula or a biased noise source, an eavesdropper could reconstruct the key without being detected. Quantum randomness isn't just a cool feature of BB84. It's the core of its security. It's the reason that even in a world with quantum computers, the keys generated by BB84 remain secure. Now, let's walk through the BB84 protocol step by step and see how a key is actually created from individual photons. Everything you see on this slide represents a single run of the protocol. One where Alice sends a sequence of bits, Bob measures them, and together they extract the shared key. Starting at the top, we have the quantum channel. This is where Alice sends one photon at a time, each one carrying a bit encoded in a specific polarization, horizontal, vertical, or one of the two diagonal states. The symbols along this line show those polarization states. Remember, these aren't just graphics. In a real quantum system, a single photon physically carries that orientation. Now look at the row labeled bit sequence. These are Alice's raw random bits. She generates them using true quantum randomness, meaning the values are not derived from a formula or a seed. They're fundamentally unpredictable. Below that is the photon polarization row. This is where Alice takes each bit and encodes it into a photon using one of two possible bases: the rectilinear basis, represented by the plus sign, or the diagonal basis, represented by the cross. For example, a 0 in the rectilinear basis might be a horizontal polarization, while a 1 might be vertical. In the diagonal basis, a 0 could be 45 degrees or 135 degrees. Because Alice chooses both the bit and the basis independently at random, each of the four possible polarization states occurs with equal 25% probability. The next row shows the exact basis Alice uses for each photon. These choices are also random. For every bit she wants to send, Alice flips a metaphorical quantum coin to pick the basis. She does not coordinate these choices with Bob. Next, we have Bob's bases, the row in yellow. Bob doesn't know how Alice encoded the photons, so he picks his own basis at random for each incoming photon. Sometimes he picks the correct basis, and when he does, his measurement matches Alice's bit perfectly. But whenever he picks the wrong basis, his measurement becomes completely unpredictable, because he's projecting the photon onto an incompatible frame of reference. Because Bob also chooses his basis randomly, each of his two possible measurement bases occurs with 50% probability, and only the matching basis cases lead to a correct measurement. Finally, at the bottom, we see the compatibility and the resulting key bits. A green check mark means Alice and Bob happen to use the same basis. A red X means the bases were mismatched and the result is useless. So after the quantum transmission is finished, Alice and Bob compare only their bases, never the actual bits, and they keep only the positions where their bases match. That sifted sequence of shared bits is the beginning of the final key. This is the heart of BB84. It shows exactly how randomness, basis selection, and quantum measurement interact. And most importantly, it shows why the protocol is secure. If an eavesdropper tries to intercept and measure these photons, her measurements disturb the system and create errors in exactly these compatibility rows. Alice and Bob can detect that disturbance instantly, proving that the channel is unsafe. But if the error rate stays low, they know the key was transmitted securely. So this diagram captures the entire BB84 process: encoding, transmission, measurement, sifting, and the creation of a shared, quantum-secure key. Everything else we discuss, error correction, privacy amplification, and attacks, builds on this foundation. Now that we've seen how Alice and Bob generate and sift their bits, the next question is, what do they actually do with that key? In this example, their sifted key happens to be 0, 0, but the length doesn't matter. What matters is that it's shared, secret, and known only to them. This key becomes part of the symmetric key material they'll use for encryption. It can seed a one-time pad, authenticate messages, or serve as the basis for an AES session key. And this is also where BB84 connects back to our Shor's algorithm video. Shor breaks classical public key systems like RSA and ECC, which means those systems can no longer be trusted for key exchange. BB84 replaces that broken step with a quantum-safe alternative. To understand what's really happening underneath, we have to step into the mathematics. In BB84, Alice chooses both a bit and a basis at random. She chooses a bit B from the set 0, 1 with equal probability, and she chooses a basis beta from the rectilinear basis or the diagonal basis, also with equal probability. Because these choices are independent, each of the four possible quantum states occurs with a clean 25% probability. If she chooses the rectilinear basis, the plus basis, then the states are simply 0 and 1. These correspond to horizontal and vertical polarizations. If she chooses the diagonal basis, the cross basis, then the states are the plus or minus 45-degree superpositions. Mathematically, these are written as ket 0, x equals the sum of 0 and 1 states over the square root of 2, and ket 1, x equals the difference of 0 and 1 states over the square root of 2. These 4 states, the computational basis states and the diagonal basis states, are the foundation of BB84. Bob also chooses his basis at random. When Bob measures in the same basis Alice used, quantum mechanics guarantees that he recovers her bit with 100% accuracy. But when he measures in the wrong basis, the outcome is fundamentally random. It's not noise from hardware. It's not a missing calibration. It's the Born rule. Measuring a state in an incompatible basis produces an unpredictable result. This is the quantum randomness we talked about earlier. Randomness that doesn't come from a formula or a pseudo-random generator, but from the structure of the universe itself. After the transmission, Alice and Bob publicly announce only their bases, not their bits, and they keep the positions where the bases match. Those matching positions form the sifted key, and that key is never revealed to anyone else. This key is not used in Shor's algorithm. It's not part of public key cryptography at all. Instead, BB84 provides a quantum-secure way for Alice and Bob to agree on a shared symmetric key, a key that cannot be intercepted without introducing detectable errors. From here, they can move on to error checking, quantum bit error rate estimation, and privacy amplification, knowing that any attempt to eavesdrop would have already produced a measurable disturbance. Now that Alice and Bob have compared a small sample of their bits, the next step is to determine whether the quantum channel was secure. They do this by calculating the quantum bit error rate, or QBER. The QBER is simply the fraction of positions in the sample where Alice's bit and Bob's bit disagree. In this example, they compared 12 positions and found 3 mismatches, which gives a QBER of 25%. It's important to understand where these errors come from. In a clean, well-aligned quantum system, Alice and Bob will still see a small number of errors just from the physics of the equipment. Detectors have dark counts. Fibers have attenuation. Polarizers aren't perfectly aligned. These imperfections create a baseline noise level, typically around 1 to 3% in modern practical QKD deployments. Anything in this range is considered normal and safe. But if someone tries to eavesdrop, specifically if Eve performs an intercept and resend attack, she introduces a very characteristic error signature. Because she does not know which basis Alice used for each photon, she guesses wrong half the time, and those wrong guesses cause measurable disturbances. When Eve resends the photon to Bob, her incorrect measurement propagates forward as errors. The result is a QBER close to 25%. This number isn't arbitrary. It's a direct consequence of the quantum measurement rules. Eve can't avoid it. Trying to read the state alters it, and that disturbance shows up exactly here, in the QBER. The next key idea comes from the Shor Preskill security proof, one of the foundational results in quantum cryptography. Their analysis shows that if the QBER stays below roughly 11%, then Alice and Bob can use classical error correction and privacy amplification to distill a perfectly secure key. In other words, anything under about 11% is mathematically recoverable. But once the QBER rises above that threshold, the protocol is no longer provably secure. There is simply too much disturbance, and Alice and Bob can no longer guarantee that Eve hasn't obtained meaningful information. In this regime, above the 11% limit, the only safe response is to abort the key exchange. So when we look at this chart, the interpretation becomes very clear. The green region on the left, between 1 and 3%, represents normal system noise. The yellow dashed line at around 11% marks the Shor Preskill threshold, the maximum error rate where security can still be salvaged, and the large red spike near 25% is the unmistakable fingerprint of an intercept and resend attack. In our example, the QBER is right at 25%, which is far above the safe limit. Alice and Bob immediately know that the channel has been compromised, and they discard the entire key. This is the power of BB84. You don't need to detect Eve directly. You detect her presence through the errors she inevitably creates. The QBER is not just a diagnostic. It is the mathematical proof that the laws of quantum mechanics protect the key. If the QBER is low, Alice and Bob can trust the channel. If it's high, the protocol fails safely. Either way, security is guaranteed. Before we wrap up, let's summarize the key ideas you should take away from BB84. First, BB84 is not just a clever protocol. It's a quantum-safe replacement for classical key exchange. Classical systems like RSA and ECC rely on mathematical assumptions, and those assumptions collapse under Shor's algorithm. BB84 replaces that vulnerable step with a physical process that cannot be broken by computational power. Second, the security of BB84 comes from incompatible measurement bases. The plus and cross bases are not just symbols. They represent fundamentally different orientations in quantum space. Any attempt by an attacker to measure a photon in the wrong basis irreversibly disturbs the state, and that disturbance becomes visible to Alice and Bob. Third, randomness is essential. True quantum randomness prevents predictability and ensures that every bit and every basis choice is unbiased. Classical pseudo-randomness can be reproduced. Quantum randomness cannot. That unpredictability is part of what gives BB84 its strength. Fourth, errors reveal eavesdroppers. A secure system still has a small amount of noise, typically 1 to 3%, just from the hardware and the physics. But an attacker introduces far more disturbance. These errors accumulate into the quantum bit error rate, or QBER, which functions as the alarm system of BB84. If the QBER is low, the channel is clean. If it rises, someone is interfering. Fifth, the Shor Preskill security threshold provides a mathematically proven boundary. As long as the QBER stays below roughly 11%, Alice and Bob can recover a perfectly secure key through error correction and privacy amplification. But once the QBER exceeds that limit, the protocol is no longer guaranteed to be secure. And if an attacker performs a full intercept and resend attack, the QBER jumps to around 25%. A clear, unmistakable sign of eavesdropping. Finally, remember that BB84 produces a symmetric key, not a public key. It's meant for encryption methods like AES or one-time pads, not for Shor's algorithm itself. BB84 gives us a quantum-safe way for two parties to agree on a shared secret. So the big picture is simple. BB84 gives us the key. In the next video, we're going to look at how attackers try to break the systems that implement it. Not the physics itself, but the devices, the timing, the detectors, and the engineering realities that can open the door for quantum hacking. Thanks for watching this presentation on the BB84 Quantum Key Distribution Protocol. If you found this helpful, make sure to like the video and subscribe to the channel. It really helps us reach more people who want to understand quantum security at a deeper level. We've got a lot more coming: real-world quantum attacks, Shor's algorithm, quantum hacking demonstrations, and full breakdowns of how these systems work under the hood. And folks, please check us out on the web at specterai.ai. We have 55 AI-proctored labs with real-world scenarios that will really cement quantum security in your mind. Each of the 55 labs is described specifically in our books. Check them out on Amazon. There is the student manual, which describes each problem in detail, and an instructor's manual, which describes each solution as well as the Python programming. So stay tuned, share this with anyone who's learning quantum computing or cybersecurity, and feel free to leave questions or suggestions in the comments. This is Specter AI. Thanks again for watching, and we'll see you in the next video.